Hi everybody, happy Wednesday. This is lecture 20. We're going to be discussing Stewart section 3.5, derivatives of inverse trig functions today. On Friday is exam 2, covers through section 3.5, does not cover section 3.7. We'll be discussing section 3.7 in class on Monday. Here you go. Before we start, I want to point out something about the online book. So, remember that on all of my quizzes and exams, I have a mix of problems. I have problems that are just like something that we did in class. I have problems that are just like something that you did in recitation, but we didn't do in class. I have problems that are not like something from class or recitation, but like a book example. So, you want to be reading the book. Now, remember how you get to the book. You go to the Canvas page for our course. And then once you get here, you click, rather than clicking on one of these individual homework assignments, you click on this link for WebAssign for Stewart's Essential Calculus. That brings you here to the WebAssign page for the entire course. Once you get here, you'll be able to see all of your assignments, not just one at a time. But you can also see the ebook on the far left menu. On that menu on the side of the left side of the screen is a link to the ebook. Now, viewing an ebook in a web browser is not great. If you have an iPad or a phone, there's actually a Cengage, that's the publisher. There's an app you can download for an Apple device or for an Android device that will let you, there's an ebook reader that will work with our course. So once you download that app, you log into your Cengage account in that app, and then you have a much better ebook reader. If you try to read this book in a web browser on your phone, it's going to be bad. And even on your iPad, even if your iPad's big. Now, if you are reading it on a laptop, I want to point out a couple of things. If we look at what we're going to be working on today, notice how little I get to see here. There's just this ridiculously narrow stripe of stuff. It's like you're looking through a little Halloween costume. And look how much wasted space there is up at top. I've got 3 rows of stuff that I'm stuck with. That little menu bar across the top, and I've got the tabs, I've got the address bar. But on a Windows machine, if you hit F11, F11 toggles between full screen view and then regular view. Regular view, I'm stuck with that ribbon of stuff across the top. If I hit F11, it gets rid of that stuff across the top. That significantly increases the real estate that you can actually read. So if you're reading this on a laptop, it suggests that you learn. And I don't know what the keyboard button is for a Mac computer, but it would be the same sort of thing. All right. So meeting part 1 is introducing the inverse trig functions. The first thing I want to do is I want to remind you of the idea of an inverse function. the idea is if f of x is 1 to 1, it has an inverse function. Which is denoted f superscript -1 of x. And you get the graph of the inverse function by interchanging the xy values on the graph of f. So for instance, we did this with y equals e to the x. Its graph looked like this, and then we interchanged x and y, and we ended up with this graph. This is the graph of the inverse function. So this is f of x equals e to the x. This is f inverse of x, which is ln of x. Now, what if we try this? And remember, with this function, the domain is all real numbers, and the range is y greater than 0. On this function, the domain is x greater than 0, and the range is all real numbers. So the domains and ranges get interchanged as well. So what if we try this with sine of x? Of course, with f of x equals sine of x, the domain is all real numbers, and the range is the numbers from -1 to 1, inclusive. So here's the graph of y equals sine of x. Notice that this function is not 1 to 1. I'm going to draw a dotted line through here. So not 1 to 1. It fails the horizontal line test. Now, what if we try the trick of interchanging the x and y coordinates? So this is f of x equals sine of x. So if I interchange x and y, I get this graph. This graph is not the graph of a function. It fails the vertical line test. So the deal is, there is no inverse function for this function. For the sine of x function, the basic sine of x function does not have an inverse function. So what we do is we introduce trig functions with restricted domains so that we end up with a function that is 1 to 1. Now the bad thing of this, so it's a great idea. The bad thing is the mathematics community uses the same notation for the function with restricted domain. So that sine of x function does not have an inverse function. There's just no question about it. But I'm going to introduce another function that's obtained from that does have an inverse function. So what I call restricted trig functions and their inverses. So first of all, we have, for this function, we have sine of x restricted to the interval minus pi over 2 with the endpoints. So it's a different function. So its graph looks like this. So it goes through pi over 2 comma 1, and it goes through minus pi over 2 minus 1. Its domain is minus pi over 2 to pi over 2, including the endpoints, and its range is the interval minus 1 to 1, including its endpoints. This function, if you say all these words, sine of x restricted to that interval, that function is 1 to 1, so it has an inverse function. So since that has an inverse function, I'm going to introduce it. I'm going to use the notation for inverse function. So it's denoted this way. Now, since this function does not have an inverse function, this is not a function. So I can use this symbol for the inverse function of this. This is not the inverse function of that. That doesn't have an inverse. This is the inverse function of that. So if you're not confused by this, you're not paying attention, because this is confusing. It's bad notation. They really ought to come up with, when I do this, if I don't have to use this book, I use capital S, capital sign for the restricted one, and capital sign inverse for the inverse function, to distinguish it from that function. All right, so I know how the graph looks. I just interchange the x and y coordinates. So instead of pi over 2 comma 1, this graph goes through 1 comma pi over 2. Instead of negative pi over 2, negative 1, this goes through negative 1 comma negative pi over 2. Furthermore, this graph flies into this point horizontally. This graph flies into this point vertically, like that. The domain is negative 1 to 1, the thing that was the range of that graph. And the range of this graph is negative pi over 2 to pi over 2. Let's do this again for cosine. So the cosine graph we restrict in a different way. We restrict it to the interval from 0 to pi. So its graph looks like this. So it goes through 0, 1. It goes through pi negative 1. It goes through pi over 2, 0. Its domain is from 0 to pi with the endpoints. Its range is from negative 1 to 1 with its endpoints. So again, the original cosine function does not have an inverse function, but this thing does because this is 1 to 1. So I have the inverse function just denoted cos inverse of x. It's the inverse of this. So this graph goes through, instead of 0, 1, goes through 1, 0. And instead of pi, negative 1, it goes through negative 1 pi. And instead of pi over 2, 0, it goes through 0 pi over 2. Now, you might think these are just connected by a straight line because there is a straight line that goes through them, but it's not. It's all these points with their x, y coordinates flipped. So this graph goes into this point horizontally, so this graph comes into this point vertically. So the graph of this function looks like this. The domain and range are those things switched. Like that. There are a bunch of reasons why I find this section really useful. The calculus actually is the least useful in my mind. What I find useful is that it is a reckoning that makes us go back and review a bunch of other stuff that we're always a little bit shaky on stuff the first time through. So it gives us another chance to look at our trig functions. So let's think about the tangent function. Again, the tangent function is not 1 to 1. It's periodic. So let's restrict it. In this case, we have to restrict it to an open interval. So the graph looks like this. It has a vertical asymptote at x equals pi over 2. It has another vertical asymptote at x equals minus pi over 2. And it looks like this. It goes through pi over 4 comma 1 because tangent of pi over 4 is 1. And it goes through negative pi over 4, negative 1. Its domain, as I mentioned, it's restricted to the interval from negative pi over 2 to pi over 2 without the endpoints, because tangent is not defined at those values. And then the range is all real numbers. All y values are possible. So this thing is 1 to 1. The tangent function would keep repeating, would not be 1 to 1, but if I restrict it to that domain, it is 1 to 1. So the restricted function does have an inverse, which is denoted just tan inverse of x. So all this stuff gets interchanged. The asymptotes, instead of x equals minus pi over 2 and x equals pi over 2, become y equals minus pi over 2 and y equals pi over 2. And the graph looks like this. And instead of going through pi over 4 comma 1, it goes through 1 comma pi over 4. and so on. The domain of this function is all real numbers. The range is that set. Which is an open interval without its endpoints. Now, this graph, tan inverse, is you're not going to see that graph very much. How many of you are in a biology-related field? How many of you are in chemistry-related field? How many of you are in a physics-related field? All right, so all of you are going to deal with a function that looks like this but is not this. We're going to come to that later in the hour. Now, I had a student come to my office today, had a question about notation. There's often very subtle notation in math. It's used precisely, and if you read it, it makes sense. And there's often very subtle notation in math that if you read it precisely, is just obnoxious because it's just stupid notation. And unfortunately, with inverse functions, there is this sort of thing going on. So for instance, tan x and arctan x mean the same thing. They're the inverse function for tangent. Now, that means 1 over tangent of x. Which is a different thing. So tan inverse of x does not mean tan x raised to the negative 1 power. Now I think the way I've written this is pretty clear. Something raised to the negative 1 power means this. Problem with this is that a lot of students will read this and they'll think this, and that's bad. Now, it gets so this is sort of precise symbols. But this is, the standard way that you denote an inverse function. You put the function's name and you put a superscript -1 right next to the function's name. And that means something else from what this means. Now, think about this. What does that mean? Well, there's really no ambiguity there. That would mean tangent of x to the second power. Here's some really bad common notation. That, or sine squared x, or cosine squared x, to mean tangent of x squared. The reason that this is terrible is because if you think that this should mean the same as this, then why doesn't this mean the same as this? It's just asking for trouble. If you write this kind of symbol meaning this, then you're asking for trouble, because you're going to look at this and you're going to think, well, this also means this, and it just doesn't. So you'll notice that in class, I always do this dorky thing, which they don't do in the book. The book writes secant squared x. That's what the book does. I don't do that. I always do that, because I think it should be clear. If we want to say that the thing is being squared, just show that you're squaring the function. Because I want to reserve the use of this kind of exponent. I want to reserve it for just one special use, this thing. Okay. All right, cancellation laws. Remember, the cancellation laws have to do with the relationship between a function and its inverse function. It's just that simple. If you compose a function with the with its inverse function, you just get what's called the identity function. Except it's not actually that simple. This is only true when x is a number that's allowed to be plugged into the restricted sign function. So this is only true when x is in that domain that's allowed to be plugged into the restricted sign function. Otherwise, you can't say this. And this is only true for x's that are allowed to be plugged into the inverse function. And so forth. There are similar cancellation laws for sine, for cos inverse and cos, and for tan inverse and tan. I'm not going to present them, but you get the idea that it's trickier than you might think. All right, so over here I'm going to start. I'm going to illustrate that using these inverse trig functions can be more subtle than you might think because of that. So sometimes a unit circle drawing is handy. So here's example 1. This is similar to 3.5 number 5. Find these values. A, sine inverse of sine 5 pi over 3. So look, it's one of those babies. Sine inverse of sine of x is just x, except it's not. This is not an x value that's in that nice domain. So what you have to do is I find it useful to, first of all, make a unit circle. And the reason is because 5 pi over 3 is one of our famous angles. So I'm going to put that here. Now, what are the coordinates of this point? Who can give me these coordinates? Hello, everybody? Famous point. Yeah. Right. 1/2 negative square root of 3 over 2. Now, using that information, what is sine of 5 pi over 3? Yeah, so this is going to be sine inverse of negative square root of 3 over 2. Now, the thing is, the sine inverse function has a range. The range of the sine inverse function is from. Well, this means the angle whose sine is square root of 3 over 2, but it's got to be an angle that's somewhere on this arc. Those are the angles that we can get out. Those are the angles that are in the range of the sine inverse function. So when I do this operation, it's got to be one of these orange angles. Now, what's the orange angle whose sine is negative root 3 over 2? Oops, I'm sorry. Wrong color. Wrong arc. It's supposed to be this arc. The sine inverse function has range. Remember that has domain negative 1 to 1 and has range negative pi over 2 to pi over 2. So the only angles that I'm allowed to consider are these orange angles. So what's the orange angle that has a sine that's negative square root of 3 over 2? Exactly. So sine inverse of sine of x was not just x. It's something else because of this problem with the domain. Now, B, how about cos inverse of cos 5 pi over 3? Well, what's cosine of 5 pi over 3? Yeah, so we're doing cos inverse of 1/2. Now, what is that? Well, for the cos inverse function, the range, I'm not sure if you're going to be able to see this. Can you see the green arc? Those are the angles that we're allowed to, that are going to come out of the cos inverse function. Its range is 0 to pi. So what's the green angle whose cosine is 1/2? Exactly. So for cosine, what we're interested in is this angle, pi over 3, because this point is 1/2 radical 3 over 2. So that green angle is the only green angle that has a cosine that's the number 1/2. So again, cos inverse of cos x is not x. And it's not even the same thing that we got for sine inverse of sine x. So these domain issues and range issues can send you on a goose chase. Sometimes a right triangle drawing is useful. So here's an example. This is similar to 3.5 number 9. Find the values. Or I should say, yeah. So A. So this is asking us to find the tangent of, well, this thing here is the angle whose cosine is x. So it doesn't mean cosine of x, it means the angle whose cosine is x. So we're talking, so this stands for the angle. Well, it's helpful to draw a picture of an angle whose cosine would be x. We don't know a value of x, so we can't use a right triangle. We can't use the unit circle. It does us no good. The unit circle is only good when we have famous values. So I draw a right triangle, and I put an angle here. I'm going to give it the name theta. And I want that angle to be an angle whose cosine is x. Now remember the SOHCAHTOA business? Well, how do you compute the cosine of an angle in a right triangle? Adjacent over hypotenuse. So I need adjacent over hypotenuse to equal x. The easiest way to get that is to just have an x for the adjacent and a 1 for the hypotenuse. So that's a picture of an angle whose cosine is x. Now I need to figure out the tangent of that angle. Now how do you compute the tangent of an angle?
Opposite over adjacent.
Yeah. We have to compute opposite over adjacent. Dang it, we don't have the opposite side here. But we can figure it out, right? We have the Pythagorean theorem. We get x squared plus opposite squared equals 1 squared. So opposite equals square root of 1 minus x squared. So that is that side. So the tangent of cos inverse of x is that divided by that. Isn't that cool? I'm always telling you about stuff that I could not remember from, that confused me in my undergraduate classes. But this thing I remember was really cool. I figured out, oh, you can make these triangles and you can figure out all this stuff that looks really complicated. So I can't stress enough the value of doing this. B. Cos tan inverse of x. Cos of tan inverse of x. Now remember what this means. This means the angle whose tangent is x. So for this, we need a picture that shows an angle whose tangent is x. So I'm going to make a new picture. So this is theta. I need it to be such that the tangent of theta equals x. So what should I do in this picture to make it that way? Yeah. Because tangent is opposite over adjacent. So that's the cheapest way to get an angle whose tangent is the number 1. Now, the cosine of an angle, as we've seen before, is, oh, actually, we haven't seen before. What is, in terms of the triangle, what is the cosine of an angle? Actually, we have seen it. This is adjacent over the hypotenuse. Okay, well, the adjacent's easy. That's just the number 1. But what's the hypotenuse? Well, remember the hypotenuse squared is 1 squared plus x squared. So the hypotenuse is square root of 1 plus x squared. All right? So that's part 1 of the lecture, introducing the inverse trig functions. Meeting part 2 is derivatives of the inverse trig functions. So remember the well, I'm going to remind you of the formula for the derivative of an inverse function. This was from section 3.1. Remember I said the content in today's lecture, the derivatives of these inverse trig functions, is not as important as the stuff that it's going to make you review. So there's a symbol for the inverse function. Here's the symbol for its derivative. F inverse prime is 1 over f prime of f inverse of x. And this is true anytime the denominator is not 0. So let's apply that to try to find the derivative of sine inverse of x. So sine inverse prime of x. So sine inverse prime of x, according to that, is 1 over sine prime of sine inverse of x. But what is sine prime? Remember, that's really an empty function. Sine parentheses prime. What's the derivative of sine parentheses? Cosine parentheses. We're dealing with an outer function that's empty. So what we need to do is 1 over cosine of sine inverse of x. Okay, well, we've got a situation where this stands for the angle whose sine is x. So I need to draw a picture of an angle whose sine is x. There, I did it. That's a picture of an angle whose sine is x. And so what is the cosine of that angle going to be? Well, it's going to be adjacent over the hypotenuse. Well, what is that? Well, hypotenuse is easy. It's just the number 1. But what's the adjacent side? The adjacent is going to be square root of 1 minus x squared. Because this side plus this side equals that side. This side squared plus that side. Well, let me just do this. ADJ squared plus x squared equals 1. So ADJ squared equals 1 minus x squared. That's really 1 squared. That's the Pythagorean theorem. So the adjacent side squared is 1 minus x squared. So the adjacent side is the square root of 1 minus x squared. So this ends up being 1 over square root of 1 minus x squared over 1, but that 1 in the bottom doesn't matter. So there's our first rule. Sine inverse prime is that baby. Now similarly, cos inverse prime, if you go through an exact same thing, the only difference is when you do cos parentheses prime, you get the negative of sine parentheses. So the end result ends up being that the derivative is the exact same derivative but with a minus sign. Negative 1 over the square root of 1 minus x squared. There's one more I want to do. I want to find the derivative of the arctan function, or the derivative of tan inverse. So tan inverse prime of x, I use that formula, I'm going to get 1 over tangent prime of tan inverse of x. Now what's tangent prime? So what would be the derivative of tangent of x? Yeah, which I would say is secant of x squared. So what would be the derivative of tangent of parentheses?
Secant of parentheses.
Wonderful. Secant of parentheses squared. So that's what that is. So this is going to be 1 over secant of tan inverse of x, that whole thing squared. Now we're going to need to make a triangle here. This symbol stands for the angle whose tangent is x. So we'll make a triangle. There's a picture of an angle whose tangent is x. Now what we need is the secant of x. So now we can write this more simply as cosine of tan inverse of x being squared. Instead of 1 over secant, that's just the same as cosine. So what's cosine of tan inverse of x? Well, that's going to be adjacent divided by the hypotenuse. And then that's going to be squared, because that whole thing is squared. So what's the hypotenuse? Well, the adjacent is 1, the hypotenuse is square root of 1 plus x squared, but then this whole thing is squared, so I get that. The derivative of tan inverse of x is 1 over 1 plus x squared. So it's a very different looking formula. Now, we have just a few more minutes. I want to do an example, but before I do that, I want to make sure that we look at the graph of tan inverse of x again, and look at the graph of this thing. So there's the graph of f of x equals tan inverse of x. Now we just found that f prime of x equals 1 over 1 plus x squared. Turns out that this graph looks like so. And so we get from here to here by taking the derivative. Now I'm running out of time, so I don't want to consider putting tangent lines on this graph and seeing why this is believable from a graphical standpoint. But I want to point out that this looks like a very famous graph. The thing is, it's not the famous graph. The famous graph is called the bell curve. It looks just like this because it's shaped like a bell. Again, if you're just going to make a crude graph like I'm doing, the bell curve looks just like it. So if the bell curve looks like this, and you ask, what's the function whose derivative would be this? It's going to be a function that looks like that function. But the thing is, this is really famous. It shows up in all the sciences. But the thing is, there's no formula for this graph. It's a really famous thing. That there's a formula for this, but there's no formula for this. We'll learn about this later in the course. So this is going to come back. All right, I have like a minute left. So examples, find the derivative of tan inverse of x cubed. Okay, well, the inner function is x cubed, so the inner prime is 3x squared. The outer function is empty. It's tan inverse of parentheses. So the outer prime is going to be empty. One over 1 plus parentheses squared. So when I put all those things together, I get 1 over 1 plus parentheses squared. I put my original inner function back in there. And then I multiply by 3x squared. On the other hand, if I do the derivative of tan inverse of x, that thing cubed, well then my inner function is a function of x that's tan inverse of x. So its prime is inner prime of x, which is that baby, 1 over 1 plus x squared. My outer function is empty, it's parentheses cubed. So my outer prime is 3 parentheses squared. So when I put all this stuff together, I have to get my outer prime, which is 3 times parentheses squared. I have to put my original inner function back in there. And then I have to multiply by my inner prime. So the moral is, once we've got these funky new derivative rules, we use these things just like we have used other derivative rules. So sometimes you use things in their empty version, and look how different this played out from this. Okay, sorry to keep you a minute late. Study hard. Make sure you signed in. If you didn't sign in, please find the sign-in sheet. Yeah.